Hello to everyone joining us from everywhere around the world. I am Carlo, and today I'm going to be talking about relational databases in the Wolfram language. So, first of all, what's the idea of this talk? The idea is to start working with relational databases. What are relational databases? What everybody calls SQL databases, except SQL is actually just a query language, and we will not be using SQL for the most part. We're going to be using the entity framework. Some of you might already know from the built-in entities, and but to query your own databases. Why is this interesting? This is interesting because SQL is a very old and proven technology that's used basically everywhere. That's been around for about 40 years. It's a very solid standard, and it's very likely that if you have a large amount of structured data, it's going to come in the form of a relational database. So basically, the order in which I'm going to explain things today is I'm going to get started with some philosophy, not philosophy in general, but the philosophy of how we decided to expose database querying functionality in the Wolfram language. And then I'm going to go and talk about classes of entities, how to perform inspection on external databases, how to perform queries, how and what relations are. And then if we have time, I'm going to go into SQL queries, which can be done in a couple of manners. And then I'm going to answer questions sometimes live as you ask them, and sometimes at the end, depending on the question and on how much time I want to give to it. So first of all, let me introduce you to entity value. Entity value is a function that you might have seen using in built-in entities, or you might have used implicitly, because whenever you type something like entity city Rome, Italy, population with, open square bracket after the entities, you're actually calling entity value. It's a shorthand for that. And so entity value is the main resolver of entity queries. And it takes first argument, which represents a class of entities or a single entity, or a list of entities, which is also a very explicit class of entities. And it's fully inert and symbolic, represents all the rows in the data. So if we're talking about countries, it's going to be something which represents, say, United States, France, Italy, and Burkina Faso, for example. The second argument, entity property, which is also usually plural. So it could be an entity property, a class of entity properties, or a list of entity properties, are what people who have worked with databases and know the algebraic way of talking about this stuff is what we call a projection. So it represents the columns. So it's asking not like, say, United States or Italy, but things like population and say area or capital city. So in general, you want to see this as like some kind of two-dimensional data, which is made of rows and columns, and so it forms a table. So first argument is going to represent the row side, and the second argument represent the column side. Resolution will only happen once you call entity value, and so the arguments to entity value are all inert and symbolic. And this is very important, as we're going to see later, because it's part of the principles of the Wolfram language to, whenever possible, have symbolic representation of things. And having symbolic representations of things as things that don't evaluate, such as, for example, an equation or a polynomial in mathematics, or in this case, things that do exist in the external world, is what makes it possible to manipulate data and code as if they were on the same level. And this is a very important language feature, specifically of the Wolfram language. We will try never to use entity list, because entity list is very often unnecessary. Entity list is a function that many of you might have used because entities have nice yellow boxes. And so sometimes you're asking entity list of entity class countries G8, and you want to know what the countries in the G8 are. But really what you're asking there are names of the countries. So that in the end is still a call to entity value. So there's usually no need to perform this call. And what we achieve by not performing needless calls to entity list is the fact that every single call to entity value is a single SQL query. Now, why is this important? This is important because if we're talking about countries, it's not really a domain of human knowledge that changes very quickly. The last time a new country was created was probably in the orders of years ago. On the other hand, maybe you are performing some data analysis on an e-commerce website which has new orders being created and dispatched at millisecond intervals. Modern databases can be massively parallel and accessed by thousands of people at the same time. And so the fact that one entity value call is a single SQL query is a very good thing because it preserves atomicity of the query. So you can be sure that the data doesn't change from when you start performing the query and when you end the query. And so the data will be consistent. On the other hand, if you say, oh, I'm going to do entity list first and then perform the query, maybe there's a second of network latency between one and the other. And in the meantime, the data has changed and you're trying to query entities or rows of the database that don't exist anymore. So just to recap, two arguments which represent rows and columns of the database, atomicity of the queries, and let's try never to use entity list. Okay, so what are these classes of entities? There are a number of heads. I will not call them functions because they're fully symbolic and don't evaluate, which end with entity class in the language. So these are entity class itself, which is something that we've inherited from the people who have worked on the built-in entities, and it can do a number of things, including basic filtering and sorting. So you can ask for things like, give me all the countries where the population is greater than 1 billion, with a very nice and concise rule syntax. And you can also try and sort things by saying things using constructs like also a rule-based syntax. However, if you add more things to entity class, at some point you will reach a point where you cannot express your query anymore. In particular, if you have multiple filters, all the filters in entity class are ended together. There's a conjunction. If you want to use disjunction or not, or other logical constructs to filter, you're better off using filtered entity class, which lets you filter by a function. So in some sense, it works a little bit like select in the language, except again, it is completely inert, whereas select, if you were to use select on any expression, select would evaluate eagerly, immediately, and break things. So it's a representation of a filter on your data. It's not the evaluation of that. Extended entity class can be used to add things like extra columns done by calculations from the other columns, or they can even be constants. So for example, if you have a class of countries and you have the population for all of them and the area, you can calculate the density and use it as an annotation. So basically the extended entity class will just work like the inner entity class, but will have extra properties that you can add. Sampled entity class pretty much works like take, except that in SQL, there is no guarantee that the results you get are going to be always the same if you don't specify an order. And that's why usually sorted entity class is better than sampled entity class. Sampled entity class might return the same thing twice, but it's not necessarily the case. But it's very useful. Sampled entity class is very useful for peaking. Say you have a huge amount of data and you really don't know what types they are, what values they are, and you just want to return the first 10 rows to see what's in it. Sampled entity class is your guy then. Well, sorted entity class works like sort by and corresponds to the, so these things you see in all caps and parens are for the folks here who already know SQL and want to know basically what to use to achieve this in SQL. So aggregated entity class is very powerful, and it has two versions, two-array version, so two-argument version that will perform full aggregations on the data. So you take the whole table and you compute the total of a column, the mean of another, and the standard deviation on yet another. The three-argument version will first do groups and then aggregates on those groups. So in a way, it works like the Wolfram language group by, except it's not hierarchical. And then there is a combined entity class, which is like join across in the Wolfram language and supports things like join. Then there's union, intersected, and complemented entity class, which are used for doing set operations on entities. The beauty of these things is that all of these guys take entity classes and return entity classes. They form a nice algebra in the space of data transformations. Most of these take one entity class and return one entity class, except combine them below, which can take more than one. Combine, join usually takes two, and then union, intersected, complemented can take 1 to n of them. So moving forward, unless there are any questions or clarification, people want to interrupt, I am looking at the chat, or at least a version of this chat. Okay, yeah, as I was saying, each class of entities takes another class of entities and return a class of entities. Everything is symbolic. And the other cool thing is that, which I forgot to mention earlier, but luckily it's written here, that you can know what columns this table will have. You can know what properties this table will have without actually performing any execution. And so if we go back here, filtered entity class will have the same properties as the entity class that it has eaten, whereas extended entity class will have a few more depending on what's in the second argument. Sample will have the same, sorted will have the same, and so on and so forth. So it's kind of a cool system because we ourselves use the system internally to reason about what things will be available when you ask for entity properties. It's something that you can manipulate and observe entirely symbolically. Okay, so but now let's get to a real database. So in the examples that follow, I'm going to use mostly for your sake an example database that is shipped with the Wolfram language and that you can find in example data. And throughout the documentation, all the examples use this database. So basically, when I evaluate this function, relational database, basically, relational database constructs itself and builds a nice object which has a number of it has nice boxes that you can use to check out what's inside. But while it's really nice to be able to, click through things, it's much nicer actually to perform, ask basically the scheme of the database questions programmatically. So once the object is constructed, we can ask for properties. And basically we can ask what the tables are in the database. And all these things are still in the SQL realm. All these things use SQL type language. We haven't yet translated it into something nice that will look familiar to users of the Wolfram language, but it will still be useful for people who are, say, need to talk to their database administrator and say, this thing isn't working because I don't see this. And then they can use database talk with them. So after the top level properties, there are properties that pertain to tables. And you can list them this way. And then you can get down to the columns that each table has. And then each column itself has properties. And so if you take these properties, you'll have things like, so just to show you, for example, native type string is what the database saves as the type for string, which is, you see, this all caps thing that it's not very useful for us, Wolfram language user, we're used to either having untyped code, or if it's typed for things such as the compiler or forms and so on, the types are much better curated. So yeah, so this is the how you query things, how you inspect a database. If you don't want to use the internal example database, what you can do is always here, you can use either database reference, which is a function that takes an association which is constructed with a bunch of things in it, such as the host and name of database, username, password, and so on and so forth. Or you can use the magic string thing like Postgres, semicolon, / and then username, @ password, colon, etc., etc. No, it's username, colon, password, @ host / name of the database. So I will parse that magic string for you, and then you can access external databases. Of course, we haven't included many examples with external databases because external databases that are directly exposed to the SQL endpoint are very rare, because it's expensive to maintain them, and it's also kind of dangerous to expose an SQL endpoint directly. But usually, if you are in an organization which has big, data lake of some sort, you will have access to the database. So yeah, so I'm getting questions on about writing to databases. Is it coming in 13.3? No, it's not coming to 13.3, but we will be very happy to add it. In fact, we have an internal version. Please make noise to your support for new features about this. Also, windowing functions. I will show a way to do windowing functions in later slides, which is not entirely native, but it can be done. The problem with windowing functions is that it's not entirely standard in SQL dialects, so it's difficult to have a common interface for this kind of stuff. But we'll get to that. Again, if you want new features in this, it's a good thing to just tell support we need this, and it will bubble up to us or bubble down depending on where you think support is. Okay, so how do you get things from a state of raw SQL lingo into something that the Wolfram language will understand? The way to do that is to wrap the database into the relational database object with entity store. An entity store will construct this other very nice boxes thing, and where I'm going to show you that there's a couple items which look different, and so I'm going to tell you what they are. So basically, whenever you see something bold, that's in database lingo the primary key of the database, which is also called the canonical name in the Wolfram language. When things are underlined, these are like virtual properties that are constructed from foreign key relations, and they can be either represented as entity or entity value properties, depending on whether it's an outgoing foreign key, that is a one-to-one relation, or an incoming foreign key, which is a one-to-many relation. And so you can see, basically, if you go into products, in the products table, you have the product lines direct foreign key, which goes back to products as an anti-class value property. So once you have this nice entity store object, which has been enriched with things that make it possible to use it with entities, you can register it. And once you register it, then this thing is available to you as if it were a built-in entity. So from this point on, there's no difference in querying things like country or city and querying these payments, offices, et cetera, et cetera, et cetera. So how do we do queries? The first and easiest way to do that is you can pass just two strings. In this case, the first string represents one of the tables, so one of the entity types, and the second string represents one single property. And if I evaluate this, it's going to go to the database, which is in this case is an SQLite file, and return to me a whole column. But in general, you probably want to query multiple columns at the same time, and you can use the third argument to transform things so that they're returned as an association. So where you can use property association or entity property association or entity association, depending on how you feel like that day. Or you can use dataset if you want. There's all the things that you know and love that work with entity value with built-in entities will work here as well. So suppose now you want to say take only the offices whose country is the USA, and then take the city of those offices. This is how you perform this query. And as you can see, basically, you wrapped our condition into entity function, and this function knows how to convert common Wolfram language expressions into SQL expressions, which is a very non-trivial thing to do across different databases, different database vendors. So there's going to be one syntax for SQL under the SQLite, one for Postgres, one for MySQL, but maybe not for equals, but for other things, we had to do a lot of work to get this to run smoothly, even if we're using, if under the hood, we're using a framework that's called SQL Alchemy, which did some of the job for us, but getting to the levels of polish we wanted required a massive amount of work. Just to show you, this is the missing queue function, which is basically the equivalent of the SQL is null, which is implemented here. And this is, again, not an entirely trivial thing to do, but it works beautifully. And as you can see, what are null values in SQL get returned as missing, not available in the Wolfram language. And another thing that is cool about this example is the fact that here in the second argument, you have one named property, just like city or country, as we had before. And then the second thing is not really a property, it's an entity function, but an entity function really kind of is a property. It's just temporary property, a computed property. So you can mix and match those things to your heart's content. So as I said before, one of the cool things you can do is like these expressions are entirely inert. So if I type this aggr stays the way I typed it, doesn't do anything. And so I can now get all the properties of this aggregated entity class, which in this case, basically what am I doing? I'm aggregating by city and country, and then I'm counting the customers for each city and country. So I can perform complex queries just by applying entity value, but if I don't apply entity value, I can keep working with this thing. So let's say I want to see the thing with the highest customer count at the top. So I can sort by descending customer count. And so basically here you can see that I have taken the previous query, which was fully symbolic, wrapped it, constructed a new fully symbolic query, sort, and only at the end I have executed the database query. And so we can see that the two largest markets for this company are Madrid and New York City. And surprisingly, Brickhaven, which I don't even know where it is. Hopefully nobody here is from Brickhaven. So, so this is the data. Another thing which I mean, right now we're still using things which are like just integers and strings, but given that we have performed some type analysis on the database, whenever there's numbers, we can convert them appropriately, and whenever there's dates, we can also, perform date operations on them and return them as date objects to the Wolfram language. So all that part of which is always, there's always a little bit of an implicit mismatch between the database and the language you're actually doing your business logic in with taken care of, as you would expect. Now, one interesting thing for those of you who well, I'm going to answer a question because otherwise I'll get distracted. Seth Chandler on the stream is asking whether this operation can be pipelined with /* notation. And this is a question he's asked me in person a few years ago. And I'm not a big fan of the /* notation because I feel that you end up with code that reads at the same time, left to right and right to left. But I think Seth's style of coding is always more using like /* rather than a normal application. And so it's always in the same direction. And this can be done because these operations are entirely symbolic. And so you just have to define basically pure functions on them, because we can't, given some of these are var, you can't really do operator forms on them. Because they would be ambiguous. But as far as I remember, I think Seth is writing a book or has written a book and maybe has just come out. And I'm pretty sure that this is a trick question and the answer is on the book. So, go and read his book. I'm sure there's interesting stuff in it because I've seen him many times at the tech conferences and he's a great speaker. So I must imagine he's also a pretty good writer, right? So anyway, what I wanted to talk about now is basically what we're doing under the hood and how these things get compiled to SQL. So basically, there is this hidden variable, which feel free to copy or screenshot, whatever, which can be turned on. And every time you perform a query, it will return the SQL that has been executed. And so in this case, as I was saying before, the function missing q gets rendered as is null. So it's asking whether the state property is null. And this creates a synthetic property. And so basically we get state as state and this expression as synthetic property 1 from offices. And so we can ask questions like, for example, this question is like, we filter the entity class of the orders and we ask what is the name of the customer that's performing an orders on Sunday. And this is a case where, since this is being executed on SQLite, it's really massively complicated to know what's happening with dates because SQLite doesn't really support dates natively, and so the order dates are stored as Unix times. And so basically this thing, which looks pretty simple in the Wolfram language, it's like a one-liner, becomes this monster of an expression with a case when to get out the dates. And so basically then it compares it to Sunday and these are our customers, and then it asks for the customer name. So there's even an extra step here because we have to get the name out of the customers. So I think this is a kind of, so if you look here, there's a whole subquery going on. So this is a pretty complicated case where we do something absolutely non-trivial by constructing the query symbolically internally and then translating Wolfram language to SQL, just to convince you that there is use in this, even if you do know how to use SQL. Okay, so this is one of my favorite parts. relations. So first of all, we need to look at the database and the schema of the database and trying to understand what the structure is. So basically, every time you interact with a well-constructed SQL database, there's going to be relations between the tables. What are relations? Relations in general are constraints in the database that tell you that a given column of the database is going to have values that depend on the values of another column, in general on the primary key of another column. And so this means that each row can reference data into another table. And this is very important to avoid duplicating data. So for example, in general, if you have two employees who work out of the same office, you don't want to duplicate the information about said office in the table that represents just the data about the employees. So, for example, I, Carlo, work for Wolfram from my home office in Rome, Italy, but there's other people working in Italy. So it doesn't make sense for the database to store under Carlo all the information about, say, the Italian tax system. We're going to have a different table with the Italian tax system, so that if the Italian tax system changes, you can change the data for me and for all the other Italians once. You don't need to go and change all the rows about Italian employees. And here we can see that there's a whole structure of things. So for example, what's a good example here? So for example, employees here belong to offices. Each employee works out of an office. And each employee also has a relation to itself. And this relation, I know, I cannot tell from the graph, but it's because I know it. It's like who they report to. So basically, this is their boss, their manager. And each employee can have multiple customers, but each customer only has one employee. That is their internal referral. So in general, this is interesting because if you look at things from the point of view of customers, each customer has only a simple relation to one employee. But an often useful question is like, who are my customers? And as an employee, whose accounts do I have to manage? And this is going to be a question that returns multiple rows, usually, possibly, maybe zero, maybe even more than one, maybe one. And so this is a one-to-many relation. So we can see it's in one line of code. We can take the schema object that we constructed before, the relational database object, and we can just basically construct a nice graph, which is computable, and we can do all the usual things that we're used to. This is just a graph object in Mathematica. So you can perform all sorts of operation on it. And what happens is that, so let's take, for example, the employees and the customers. For each of these, so for example, the employees, all employees have a reports to column, which is raw data. It's just the foreign key, and it's not very useful. It's not very computable. So what we're doing is that we're synthetically generating these new properties, which are going to be entity or entity class valued. So for example, each employee works out of an office, and I can get the office code of all the employees, and it's not going to be a very useful information because these are just numbers. But if I go and use offices, these are going to be represented as entities, which are much more computable. And I will show you later, one really cool thing that you can do is basically you can chain these things because entities have properties themselves. So for example, and I can also go the other way around. So if from offices I want to go to employees, this is the class of entities of all the employees that work out of the office, which has office code number 1. So it represents all. So it's going to represent these 111, 111 employees. And you can construct some really complicated stuff. So this is an example from the documentation that I wrote a couple of years ago, which is like, so if I run this, this gets applied to a single customer. And it's telling me that Gerard Hernandez is the sales representative for Atelier Graphique, and their manager is Gerard Bondour. So let's unpack this a little bit. So first of all, this is a giant string join. And what I'm doing is like starting from the customer, I get out the employee of that customer, which means basically, in this case, it's like their sales representative. I'm getting out first name and last name. So I'm chaining properties here. And here I'm going even crazier because I'm chaining twice. So I'm following this. Earlier, I was just following this arrow. Now I'm following this arrow, and then I'm following this arrow here. And so I'm getting out the informations about the manager. So basically, this is done automatically by us by symbolic knowledge of how the data is structured within the database. How would one do it in, let's say, halfway between using Wolfram language for this stuff and using SQL? Well, this would require a couple of joins. And so you can use, if you want to do explicit joins, you can use combined entity class twice. And here we're lucky enough where we don't need to specify much, like these joins are all simple inner joins. You don't have to say left, right, outer, and worry about all that extra level of complexity in algebra. And then we can apply this entity function to get the data out. And one thing that is really cool here is that, and this is, to my knowledge, of all the SQL frameworks I've worked with, we're the only people who can do that out of the box so easily, is the fact that, so basically here, there's, when we perform the join on the reports too, there is a potential source of confusion from the fact that there are now two employees tables that have been joined together. And there's a very simple prefixing mechanism, which is entirely symbolic and which lets you specify two different employees tables in this, and you don't have to rename all the columns by hand and all that sort of stuff. You can just refer them later as entity property manager employee, or just if there's no prefix, it's going to be just employees. So this is the base employee and this is the manager of that employee. And we take care of generating the correct SQL under the hood, but the prefixing is done entirely symbolically. And if some of you here, maybe Mohammed has used the raw SQL before, this is something which is really, really, really painful to do by hand. Another thing that is cool about the relations is the fact that you can perform aggregations without really using the aggregated entity class. So for example, in this case, what I'm doing is like I'm following a relation, which is a one-to-many relation. So for each order, there is a number of lines in the order which each contain. What I'm doing here is basically I'm taking the order details table and getting, sorry, not the order detail, the order details that correspond to the order number 10,100. And then I'm taking the price of each row and multiplying it item by item to the quantity of each row. And then I am just totaling it. And this thing actually is going to perform the correct subquery and aggregation that I need to do this. So you can reason still in ways that are very, very powerful, very close to usual Wolfram language. And under the hood, we will unpack this all for you and perform a query. So do use relations because they're very powerful. What's next? Oh, now we can talk about things like things that we do not support yet, we might not support ever, but which sometimes we need. So first example is how do we put some sort of a embedded SQL expression, a string of textual SQL, which contain things that we cannot do because, for example, in this case, this is stuff that is only supported by SQLite. and so it doesn't make sense to write the functionality, because the day you try to port your code to MySQL, it will stop working. So in this case, SQLite, you can ask all sorts of crazy things. Like in this case, we're asking, what is going to be the first, I don't remember if this is Sunday or Monday, I don't know what the, of July of this year. So we take now, we got the beginning of the year, we had 6 months, we go to July, and then we take the first, I don't know if it's Sunday or Monday. Then we can do things like, for example, in this case, one cool thing about this is that we can use the templating language of template apply, string template, and so on and so forth to bind external values out of this. So for example, in this case, we're using glob pattern matching, which doesn't work in all SQL backends, and using it to check what countries start with U. So we get yes for USA, and we get no for France and Japan and Australia, and yes for UK. Another thing is, what if I want to have a whole class that is written in SQL and not just an expression in a function? And basically here we're constructing the factorial in SQL by using recursive CTE, common table expressions, which are something that is supported by most vendors, but I think would be pretty complicated to express in a way that actually makes sense for Wolfram language user. But sometimes it's useful if you wanted for things like transitive closure, etc. So, but if you want really fully arbitrary stuff, great, this didn't work. Gotta support, but let me undo so you can see what it was doing. So if you want to write to SQL, for example, as Mohammed was asking earlier, you can create this table of developers and insert into it data and then select from it, and this will just do it. The thing that didn't work, just FYI, is the fact that I was trying to use SQLite in memory without actually creating a file, but if you put a file here, it will work just fine. Okay, so this is if you want to do completely arbitrary stuff, and you want it, it's especially interesting if you want it intermingled with the rest of the stuff. So for example, one thing that is really cool about this is that if you write an embedded SQL entity class, you can still reason about its properties. As you can see, I'm a bit slow typer today. And it has, you see, I mean, it didn't format properly, but it has two entity properties, one named N, and well, it didn't format properly because, of course, we never did it. But yeah, we shouldn't hide the fact that this comes from a query. But you can see that we get the entity properties out, and so it behaves just like any other entity class. So before I move to the next slide, I'm going, who's asking, was the decision to make the entity version of group by non-hierarchical by design? The answer, and then he says, nesting group bys enables creating indices on the fly. Well, the reason why we made it non-hierarchical is because if you make it hierarchical, then what you get out is not an entity class anymore. So basically, you lose all the nice composability features that we are used to with all the other entity classes. And so basically, the end results becomes terminal. You can't perform further computation on it. And so it was a trade-off. We decided for the sake of having a nice, consistent algebraic space where you could go from anywhere to anywhere, rather than having sinks in the space where you can't perform any more operations from. Oh, this answers your question, Alan. So yeah, so I'm pretty much done with the things I had. So if you have any other question, I'm gonna stay here for a little bit longer and see if I can answer them, given my inability to type fast today. Do we have some like elevator music to add to this so that it doesn't sound too lonely? Okay. They're telling me that there's not much in terms of questions coming, so maybe we can just close the stream here. And thank you very much, everyone who's joined us today. And I also thank the future watchers, because I think this is going to stay on YouTube. And I wish you a wonderful rest of your day wherever you are in the world. Thank you very much. Bye-bye.